Hello. So this is question number 37 from IIT JAM 2022. So we have G, a finite group of order of at least 2. So order of G has been given at least 2, minimum 2. Okay. And E denote the identity element of G. So let sigma, it's a bijective group homomorphism that satisfies the following two conditions. So one of the condition is sigma G is equal to G for G belongs to the capital G, the group. Then G is equal to the identity element. And the second one condition is sigma composite sigma G is G for all G belongs to this group G. Okay. So that has an order of at least 2. So we have to find which of the following is the correct option. So which of this following is the correct option. So we have given the finite order of at least 2. So let's check whether the order of the group G is an odd number or an even number. Okay. So from here we can see that sigma is bijective group homomorphism. So we can write sigma as auto homomorphism, right? So if we write sigma square G, it will be simply G, right? So let us have this two group. One is, so these are the two groups, so they belong to G, this one, and this is one of the function that is sigma, right? So here E is the identity element, so E will map E only, and at least 2 means E A is there, B is there, C is there. So we are considering whether this order of the group is even or odd. So this is our question. Okay. Now this is both G and E. You can see that E corresponds to E, identity element. So in that case, A, suppose let us consider G is equal to A, and A is mapping over to B, okay, and in this way, and B is mapping over to A. So we have the composite function over here. So it is saying that sigma composite sigma of G is G, right? So sigma of sigma A, it will be sigma of B, which is A. So the main thing is that if sigma composite sigma G is equal to G, then sigma composite sigma A should be equal to A. From here you can get. So A is mapping to B, A onto B and B onto A. So we can say that it is possible. Now we have to check the C, whether C can map onto C. It is not possible, right? You cannot just map C onto C. So now if we want to map C onto A, what will happen? So if we consider the mapping of sigma of C is equal to A, then sigma composite sigma of C equal to will be sigma composite C Okay, sigma of sigma c. So sigma c is mapping to A, so we can write sigma of A, which is nothing but C. But C, this C cannot map to A because A is already mapped to B and B to A, right? So from here you can see that the order of G cannot be even, and it must be odd number. This cannot be an even, right? You can get from this mapping, also you can get from the particular group in this case. So A is mapping onto B and B is mapping onto A, and C has nothing to map on. This C and C cannot happen, and C maps to A is also not possible. So this minimum of so that's at least 2. So this the order of the group G is an odd number, right? Now we have, so here you can see that A is order of A by order of B is equal to, so we can write in this way that order of A by order of B is equal to order of B by order of A. This implies that order of A is equal to order of B. Okay. So now let's check with the condition C. It is given that in C we find that the map sigma satisfies the sigma x is equal to x inverse for every x belong to this group G. So the sigma x inverse we have already, so we can write it over here. Sigma of x is x inverse, right, for all x belongs to this G, right? So here you can write, simplify it, x of sigma x is equal to E for all x belong to G, right? So there should not exist so there should not exist x belongs to G for x of sigma x is equal to E, right? So x of sigma x is equal to, is not equal to E, right? So this is the condition. So this, from here we can get for x equal to G, so that there should not exist x belong to G for x sigma x is not equal to E. So we have to find, so suppose this G is of we can consider this G as G, or G is equal to this Z of 5. So if we do this, so G is Z5. Okay, so let us, what are, how many elements are there? So this is 0, 1, 2, 3, 4, right? So here you can find that this 1 inverse. So if we do, the 0 is the identity 1, the identity element, that is E. So if we do 1 inverse, what will come? It will be 4. So 2 inverse, it will be 3. It will go like that. So if we draw two groups, like something like this, so this is one of the G where we have the 5 elements, is mapping onto G with the same 5 elements. So 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Right. So this is corresponds to 0, corresponds to 0. This is the identity element. Okay. And this is the sigma mapping. So this is also G equal to Z5, and this is equal to Z5. Right. So here you can see that, and 0 is 0 is 0, 0 to 0 is homomorphism. Okay. So if you do this, so if we do now, 1 is mapping to 2. Okay. If you consider this, this 1 is mapping to 2, so it will be 2 will be mapping to 1. Now we have the sigma x is equal to, from this we can get the sigma x is equal to x inverse, right? So sigma of 1 will be 1 inverse, that is 4. So sigma of 1 will be 4, right? Now if we consider that 1 is mapping to 2, suppose we have this first case, our is whether we check 1 is mapping to 2 or not. So now if 1 is mapping to 2, so we can write the sigma of 1 modulo 5 2, it will be sigma of 1 modulo 5. Okay. So this is plus of modulo 5 sigma of 2, right? So this 1 plus 2 will be sigma of 3, and this is sigma of 1 is, we are pointing it to 2, so this 1 2, so 3 will be 4 and 4 will be up to 3, then in this way. So sigma of 1, it is so here it is sigma of 3 to 1 plus 2, and it is sigma 1 plus sigma. So sigma 1 we have considered it is as 2, right? And this is modulo 5, sigma 2 is 1, and what is sigma 3? Sigma 3 is 4, and here we are getting 3. So this is not equal to this side is not equivalent to this side, RHS LHS, so it is not equal. So this 1 is not mapping to 2. Similarly 2 will not map to 1, right? Now let us check with the second case. So it is so this, for this case it is not possible. Now let's check that 1 tends to 3. So for 1 to 3, so if we again we are drawing this to G Z5, so the 0 1 2 3 4, 1 2 3 4, right? So now if we put this 1 up to 3, then we'll go to 1, and 2 will then go to 4, map onto 4, and 4 will map onto. So this is the condition over there. So we can write this in this form, that this, sigma 1 in our case is 3, right? It is 3 now. So if we sigma composite sigma of 1 it will be 1, right? We know that this is from the second condition, so we can write it here. This sigma of 1 is equal to 1, and sigma of 1, we know this is 3, so sigma 3 is equal to 1, right? Now if we go with the above same thing, that if we write in this manner, that sigma of 1 modulo 5 3, so it is sigma of 1 modulo 5 sigma of 3, right? So it will be modulo 4, and sigma of 1, we know that it is 3 plus modulo 5, so there it will be 1, and modulo 4 we know that is 2, and it is equal to 4. Is that equal to 4? It is not equal to 4, so we can also say that it is not equal to this 1, is cannot map on 3, so that is the same for this 3 cannot map to 1. So now let's check with this option, this 1 to 4. Let's check with this. Now if I have the to set G cell, so this is G, means this is the equivalent to Z5, so this is 0 1 2 3 4, similarly 0 1 2 3 4, so we have already 0 to 0 is there. Now 1 is mapping onto 4, and 4 is mapping onto 1, 2 is so now 2 is mapping onto 3, and 3 is mapping onto 2, right? So let's just find this thing, that so we know that sigma composite sigma of 1 is equal to 1, so sigma composite sigma of 1 is equal to 1, and it is sigma of 4 is equal to 1. So keeping the same formula, if we write that the sigma of 1 plus modulo 5 is 4, and if we put that the sigma 1 modulo sigma 1 modulo 5 of sigma 4, so what it will happen, so it will be 0, right? 1 modulo 5, so it will 4 plus 1 5, so is the identity element of 0, 5 modulo 5, so this is phi of 1, so this is 4 modulo 5 1, okay? So this sigma of 0 is equal to 0, and 5 modulo 5 is 0, so this equation is actually holding, so we can say that 1 is mapping upon 4, similarly 4 will map upon 1. So, and we already make this that 1 inverse, so this is the assumption, this is the first, so this is what we get, that phi x is equal to lambda x inverse, so phi of 1 is 1 inverse, which will be 4, right? So we can write in this manner, so in our case 1 is mapping to 4, 4 is mapping to 1, similarly 2 will go for 3, and 3 will map to 2, right? So we know that 1 inverse is 4, so putting the same thing, that phi of x is x inverse So phi of 1 is 1 inverse, which is nothing but 4. So, and we can also do one thing over here. If we don't put the 4 is in this. So phi of 1 is 1, right? So you can write that 1 multiplied by phi of 1 is equal to 0. So if we put this form as x, so x dot phi of x is equal to e. So from this relation we can get, so let it write in a more clearly. So we have the, from here we can write this x of phi of x is equal to e. So from the option you can see that, so in our case the option C will hold true, because this let's check with option C first. So it's satisfying the relation, this phi x is equal to x inverse, and you can see this x inverse. So this is, these two options are complementary. For x equal to g, we have seen that, so if we take this yes, this is our condition you can take. So this is the option C and this is the option B. So in our case the x sigma x is equal to E and x belongs to G. So C, option C is correct. So what is the option A? So for G belongs to G, there exists H, which is also an element of G, such that H inverse sigma H is equal to C, element of that group. So let us solve it also to check whether A is an correct one or not. So we have given H inverse sigma of H is equal to G, right? It is given. Now then sigma of H is H inverse, right? As per the condition 2, sigma of H will be H inverse. So if we put the value over here, so H inverse is equal to G, right? Since that G belongs to the group of G, so the H inverse will also belong to G, right? So from here we can see, since G, small g, belongs to the group G, capital G, so H will also belong to G. Since H will belong, it inverse will also belong to G, right? So this is H, we can say that H composite of H inverse, composite H inverse. So this is H and H inverse, so both are elements of G. And here you can write this, that from here we can conclude that H inverse, composite of H inverse is equal to G, right? Means it belongs to the so it belongs to G. So we can conclude that H inverse sigma of H is equal to G, right? So in our case option A is also true. So let's check which one of the options are true and correct out of the 4 options. So in our case, the question, this is question number 37. So we have A is the correct option. For each G belongs to G, there exists HG such that H inverse sigma H is equal to G, and option C is correct. And the order of the group is and option D is also correct, because the order of the group G is an odd number, not be an even number. So we have checked with that. So for question number 37, the correct options are A, C and